So, we have almost finished the dynamics part, which I wanted to tell in this course. We talked about forces, momentum, kinetic energy, we changed so many definitions and we defined new quantities like total energy and all those things, and everything comes from one clue from electrodynamics, Maxwell's equations, and that is electromagnetic waves. A wave in terms of electric field and magnetic field will travel at one single constant universal speed, which we write as small c. So, from there we could build up this big formulation of mechanics. Now, I want to go back to electricity magnetism and see how that relativity is related to these fields, electric fields and magnetic fields. You know, electric field given by force is equal to q times E, and magnetic field given by force is equal to q v cross B. Now, it is very interesting, and this question we face very frequently, that if I have, let us say, if I have a wire and this wire is creating some magnetic field, and I have a charge here which is going with a velocity v in the same direction as the current, positive charge you can assume, then because of the magnetic field there is a force, magnetic field will be into the board and then q v cross B will be towards this wire. So, this q will, this particle will deflect. Okay. So, that is the action of magnetic field. But then if I go to another frame which is also moving, suppose I have a frame which is also moving in this direction with the same velocity v. So, in that frame this charge is at rest and magnetic field does not exert any force on a charged particle at rest. And if there is no magnetic field force, then it should just stay there. Why should it go towards this wire? So, that is a dilemma many students have when they do not know about relativity. So, these are the kind of questions which I want to address today. The essential fact is that if you have electrostatics and you have relativity, the magnetism comes out of this. Suppose I have two line charges. Suppose I have a positive charge line, a linear charge, long line charge of positive charges, long line charge, and suppose the linear charge density is lambda here. And then I have a negative charge line also, a line of negative charges also superimposed on this one, just superimposed on this one, and this negative charge line that moves in our lap frame with velocity v towards say positive x axis, and the linear charge density here is minus lambda. So, equal magnitude and opposite sign, and therefore, if you look at electric field here, the electric field will be 0 and all that. Now, suppose you have you look this same situation from S prime frame. So, this is from S frame, and then if you look from S prime frame which is moving with respect to S in positive x direction with a velocity v. What happens to the linear charge density? Take 2 points, start with the positive line charge, put 2 points, 1 point here and 1 point here with some length in between, and this length is, let us say, L. Now, how much is the charge between these two? That is lambda times L. Now, if you see from S prime frame, this will be contracted because this line charge is at rest in S. So, the length, if I call this point small a, this point small b, then the length a b, this is small a point, this is small b point, the length a b is the rest length here. If you look at the same length from S prime frame, this positive charge is going in the backward direction, it is moving, and moving lengths shrink, and therefore, the length will be decreased. But the charge between these 2 points is still lambda times L, and length has decreased by a factor square root 1 minus v square by c square. So, what happened to lambda, linear charge density, that increases by gamma. So, lambda plus prime will be lambda divided by square root 1 minus v square by c square. Length has contracted, linear charge density is length, you have to divide by length, charge divided by length, and length has contracted. So, this has increased. Now, look at the negative charge line. The negative charge line in S frame is moving with a velocity v towards right, towards positive x direction, and therefore, as seen from S prime frame, this is at rest. So, again if you take 2 points on this negative charge line, and then you ask if this length is say L, what will be the length between these same 2 points as seen from S prime? That length will be larger, because in S prime frame this is at rest, and rest length is the largest length, moving length is smaller than the rest length. So, the length has increased by a factor gamma, and therefore, the charge density will decrease, and hence this lambda prime, lambda minus prime will be lambda into square root 1 minus v square by c square. In S frame, the two charge densities had equal magnitude, one positive, one negative. The whole system was uncharged, and therefore, there was no electric field. Now, in this frame, the charge densities are not equal in magnitude, hence you will have a positive resultant charge density, and that will be lambda prime, and lambda prime will be lambda plus prime and minus lambda minus prime, this positive charge density here and this negative charge density here. So, that will be lambda by 1 minus v square by c square, and then minus lambda into 1 minus v square by c square. Okay. So, lambda you can take common, and then you have 1 here, and then minus 1 minus v square by c square, and then divided by square root 1 minus v square by c square, and this is lambda into v square by c square, and then square root 1 minus v square by z square. So, this is lambda prime, this is the charge, net charge density, charge per unit length as seen from S prime. Now, if there is a linear charge density, long line charge with this linear charge density, it will create a field, electric field. So, suppose I have a point charge q here, which in S frame moves with a velocity v at some distance, let us say r from the line charge. What happens to this charge as seen from S prime frame? In S prime frame, this charge is at rest. So, in S prime frame, you have a net positive charge density. I am now drawing not this one, the net positive charge density lambda prime, and then at a distance r I have a charge q at rest in S prime. So, you will have an electric field, that electric field will create a force on this charge, F is equal to q times E, and you will have Fx is equal to 0. First let me write E. What will be E? E will be lambda prime divided by 2 pi epsilon naught r, or let us say, let us call it x direction and that is y direction. So, let me call it y, right, this is y, this is y coordinate here. So, that is the electric field in which direction? In y direction. So, j cap. So, force will be q times E. So, if I write force, it will be q times this, and lambda prime is here, remember lambda prime is here. So, we can write that also here. So, what is Fx? What is Fx? Fx is 0. What is Fy? Fy is q into lambda prime, which is lambda into v square by c square, and then divided by, this is 2 pi epsilon naught here, y here, and then square root 1 minus v square by c square. Check, lambda prime I am writing this quantity. So, q is here, lambda prime is lambda v square by c square, and then divided by square root 1 minus v square by c square, and this 2 pi epsilon naught y, which is here. So, that is Fy, and Fz is 0, and all these are in primed coordinate S prime. So, let me put prime here, and that is it. Fx prime is 0 and Fy prime is this. This is y and y prime are same, so I can leave it here. Now, if there is a force on this particle q in S prime frame, I can make use of force transformation equation and obtain what is the force on this particle in S frame, right. You remember force transformation equation? The force transformation equation is Fx prime is equal to Fx minus v by c square F dot u divided by 1 minus v ux by c square, and similarly Fy prime was Fy multiplied by square root 1 minus v square by c square, and the same denominator 1 minus v ux by c square, and similarly for Fz prime. I have to go from S prime to S. So, inverse transformation, and inverse transformations will be, remember, very simple, interchange all primed and unprimed quantities and replace v by minus v. So, if you do that, Fx is equal to Fx prime. So, I am interchanging primed and unprimed quantities, and then it is minus v by c square, this is f. So, this will become f prime dot u prime, and then divided by 1 minus v ux by c square. So, that is for the x component of force, and for y component of force, once again this will be plus, because v becomes minus v here. So, this will become plus, and this v becomes plus v. So, this will be plus v. So, plus here, and then Fy prime is equal to, or Fy is equal to Fy prime square root 1 minus v square by c square divided by this v becomes minus v. So, it is 1 plus v ux prime divided by c square, and similar expression for fz. There are two velocities involved, remember. There is a particle velocity and there is a frame velocity. This u is the particle velocity. This is velocity of the particle in S frame in this formulation. In this formulation, this is the velocity of the particle in S prime frame. And then the frame itself moves with a velocity v, so this v is there. This ux is, once again, this is the x component of the velocity of the particle in S prime frame. So, I am going from S prime to S. Now, in our case, we have this particle q and the velocity of this particle is 0 in S prime frame. So, u prime is 0, that u prime is 0, this u prime here, this u prime or this ux prime, this is 0, and hence what we have is this is 0, this is 0. So, fx is equal to fx prime, and this is 0, this is 0. So, you have fy is equal to fy prime multiplied by square root 1 minus v square by c square. So, this is the transformation equation in our case, where the velocity is 0 in S prime frame, velocity of the particle is 0 in S prime frame. Then fx prime is 0, fx prime is 0, x component of the force on this particle is 0. I have a net positive linear charge density, long line charge, the electric field will be in y direction. So, no force in x direction, fx prime is 0, and therefore, fx is 0, this fx is 0. Then fy is fy prime multiplied by square root 1 minus v square by c square. So, here it is, so multiplied by square root 1 minus v square by c square. So, this quantity will cancel out, this quantity in the denominator will cancel out by this quantity in the numerator, and therefore, fy prime will be equal to q lambda v square by c square, q lambda v square by c square, and then divided by 2 pi epsilon naught y, 2 pi epsilon naught y, this factor cancels out. So, this is fy, fx is 0 and fy is fy prime multiplied by this, which is this. So, in S frame, now come back to S frame, where the total linear charge density is 0, plus lambda and minus lambda. So, there is no electric field, but still there is a force, and the value of the force is given by this. It is fx is equal to fx prime, which is 0, and fy is equal to this much. So, you have a force in y direction, you have a force in y direction on this particle, there is no charge density, still you have a force. So, you can write this lambda into v as I. Lambda into v as I. There is a current, the positive charge line is at rest, but the negative charge line is moving. The linear charge density is lambda and the velocity is v. So, lambda times v will be the current. And then you have, so you can write this as q, this q here, and then I, this I here, and this v, one v will be there, by c square will be here, and then 2 pi epsilon naught, 2 pi epsilon naught y. Okay, where I is now the current, you do not have linear charge density, but you do have current, because your positive charges are not moving, only the negative charges are moving. So, you have a current in negative x direction, current in negative x direction, negative charge is going in positive x direction. So, that current I am writing here. So, q times v times and then I and epsilon naught c square 1 divided by epsilon naught c square, 1 divided by epsilon naught c square, that is mu naught, and hence this is mu naught by 2 pi, this epsilon naught I have written, c square I have written, and then it is 2 pi times y, and here I, and you have a q and you have a v. So, you can see, you can write this as q, this q, and then v, and this quantity if you call it b, your force is q into v into b. And if you can give directions also, if you write b in minus k direction, b vector, write b vector as minus bk cap, and this v vector as v I cap, you can immediately see that this force which is in y direction, remember this is in y direction, force is in y direction, this force will be q times v cross b. So, what we have derived is a straight current I produces a magnetic field mu naught by 2 pi I divided by y, and we have derived it from electrostatics. Here is the electrostatics, F is equal to QE on a particle at rest, and then the relativistic transformations. So, magnetism is essentially a relativistic phenomena. When you see magnets and magnetic fields, you play with magnets, you are actually observing relativistic effects in small velocity domain. You do not speed up the magnet, or you have a frame which is moving with very large speeds and this and that, but still whenever you see a magnetic field, whenever you see a magnetic phenomena, you are actually observing relativistic phenomena.